Okay, our next topic here for the routing exam is what is defined on the blueprint as Layer 3 path control, which again really refers to Layer 3 traffic engineering, where we're trying to change the path as we go from a particular source to a destination, or based on some other criteria that we are going to define. Now, the feature specifically that we're looking at now is called policy-based routing, or PBR, which takes the information that normally is not in the routing table and allows us to do a more detailed classification of how we actually want to move traffic between the interfaces. So all the routing that we've seen up to this point, whether we're doing static routing or dynamic routing with IGP or BGP, is always based on the longest match to the destination. This means that when the router receives the packet in, it looks at what the destination address field is in the Layer 3 IP header. It compares that with using a binary AND with whatever is in the routing table, and it finds whatever has the most bits in common. That's our longest match. Based on what outgoing interface the routing table says, then ultimately the packet is handed off to the switching process to be moved between interfaces and then rebuilt with a new Layer 2 encapsulation. But the key point being is that the piece of data that we're doing the lookup on is always the destination address. Now, policy routing goes beyond this by giving us some more criteria that we could do classification based on. Could be based on source address or destination address. Could be source and destination pairs. Could be the interface that traffic is coming in on. Could be the application, so we could distinguish between web traffic versus FTP traffic, or it could be a type of QoS marking. So when we're doing the actual classification, it's going to either use an extended ACL or a match interface command, which specifies where did the traffic come in on. Once we do our classification, then we decide what do we want to do with the traffic. So do we want to remark it? We could change the QoS markings. Do we want to send it to a particular next hop, or do we want to send it out a particular interface? So it's giving us more manual control over the routing policy. Two disadvantages with this feature. First off being that it is manual, so there's no dynamic communication between one router and another, how it is doing its policy routing. Second is going to be performance limitations. So for enterprise class routers like the ISRs or ISR2s, you're not going to see the greatest forwarding performance when you do PBR as you compare it to normal forwarding. Now, if you do this on like a 6500 with SUP 720, it does have hardware acceleration for the PBR process. So you'd have to look at what is the hardware that you're dealing with first before you decide whether you actually want to implement the feature. It's very, very flexible. Main problems are that it's only static, so we need to manually define the policy, and that it could have potential performance limitations. Now, the way the policy routing works implementation-wise is first off we need to do our classification. So this is either going to be based on the interface that traffic is received on or an access list that we're calling. It could be a standard list or it could be an extended list. So with extended lists, this implies that we could do any classification that is supported in the extended ACL, which would be source address, destination address, Layer 3 protocol, so is it OSPF or is it IP? For Layer 4 information, it could be TCP or UDP ports. It could be TCP flags, like the SYN or the reset. It could be Layer 3 markings, like IP precedence or DSCP. Basically anything that we can match inside the extended ACL. Now, as you can imagine, the deeper inspection you get into the packet, the more performance hit that you're going to take. So if you're matching just on source and destination pairs, you should get better performance if you're looking into than if you're looking into the Layer 4 header. So once we classify the traffic, then we define what are we going to do with the actual policy. There's two ways to apply this, either for incoming traffic on the interface, which is the IP policy command, or locally generated traffic with the IP local policy. Now, the second option is less common. You normally don't need to policy route traffic from the router itself, but you technically can if you want to with the IP local policy. Now, depending on the option that we're setting, which is going to be either to set the next hop, set the interface, set the IP default next hop, or set the default interface, it controls the order of operations from how we distinguish the policy route versus the actual routing table. So in the route map, if we use the commands set IP next hop or set interface, the policy route is checked first before the routing table. So if there's a match in the route map, that occurs before the routing table does. If we say set IP default next hop or set default interface, this is a fallback from the routing table. So we check the routing table, but if there is no match, then we go back to the policy route. So the more common application would be the first variation, where we check policy routing first and then go to the routing table, versus the other way around. Now, along with this feature, we're also going to look at some examples of the IP Service Level Agreement, the IP SLA, and enhanced object tracking. Now, we looked at this a little bit before in switching when we were dealing with the first hop redundancy protocols like HSRP, VRRP, and GLBP. But this feature can also integrate with routing, specifically policy-based routing or static routing, in order to give us some more application level awareness as to what the status of the network is, and then react based on that particular configuration. Okay, there's actually a much more detailed technology beyond this that's called performance routing, or PFR, which was previously called optimized edge routing, or OER. The performance routing and optimized edge routing features basically combine the IP service level agreement along with static routing and redistribution, where the router can make its own intelligent decision on how it wants to route traffic based on conditions of the network. So we could define a policy that says I have two ISPs. I have ISP1 and ISP2. ISP1 is guaranteeing me 60 milliseconds latency to my other sites because I'm doing voice over IP. If that particular path goes above 60 milliseconds latency, I want the optimized edge routing feature to change the routing domain so that I automatically route over to ISP2. So there's a lot of detail that you can get into with the feature. We're going to touch on just the very beginnings of the topics today, do some basic examples of doing reachability checks, and then based on those results, how we can affect either policy routing or how we can affect static routing. So the same topology that we were looking at before I have built with the layer 2 interfaces are up, IP addresses are up. I simply have eIGRP running on all of the interfaces. So there's basic reachability end to end between the devices. Now what we're going to look at here with policy routing is changing the flow of traffic as it is received either by router 2, either by router 2 or router 3 as the traffic is going up in this direction. So we're going to apply policy routing on router 2's Fast Ethernet 0/0.24 and router 3's Fast Ethernet 0/0.35. So first let's look at the current routing domain and see how traffic is flowing from router 4 and 5 up to the final destination, which is going to be router 1. So from router 4 here, if we look at our route to the destination, show IP route 10.1.1.1, it says this is known via eIGRP and it's coming from router 2. We can also see the output of the trace route there. It says to get to router 1, we're going from 4 to 2 directly to 1. On the other side of the network on router 5, we're going to its closest exit point, which is router 3. So we're going from 5 to 3 to 1 in order to reach that particular destination. So what's common about these two flows is that routers 2 and 3, they're receiving the traffic on the inbound interfaces that are coming from routers 4 and 5. So this is where we're going to apply our policy routing. It's going to be on the link from 2 to 4, as traffic is received inbound, and then the link from 3 to 5 as traffic is received inbound. So here we're going to start with a very basic policy that is going to modify all traffic that is transiting through router 3. What the result of this that I want is that when we look at the trace route, the traffic should go from 5 to 3 to 2, then to 1. So we're going to add an additional hop into the network. We're going to redirect the traffic over to router 2. But at the same time, if I were to do a trace route to, let's say, the link between router 3 and 1, I do not want this traffic to be affected. So only traffic that is going to this particular destination do I want to modify the path. Okay, also let's look at, let me see how I trace to router 2. That's actually load balanced. So we can compare this by looking at this output, so going to 13.1 versus the 1.1. So once the policy routing is implemented, this second trace route, it should have an additional hop inserted, which is going to be router 2. So the first step in policy routing is to do the classification. So what particular types of traffic do we want to be subject to the policy route? In this case, we're going to use an extended access list and classify traffic based on the destination IP. So on router 3, let's say, actually, you know what I'm going to do? We'll do it based on source and destination. So then we could see the difference between this trace route and this trace route where we're matching the source and the destination. Okay, so when we're tracing to router 1 from 5's LAN interface, it's going to insert the hop over router 2. But just the normal trace route to router 1, it's going to have the shortest path. So here we'll match on both source and destination address. So first we'll create an access list. Let's say access list 100 is going to permit any IP traffic that's coming from that address on router 5 that's going to the address on router 1. So like I mentioned, anything you can classify in the extended ACL, you can apply to policy routing. So I could say the whole segment or the whole subnet instead of just a host, or I could get more detailed up to the application level. So anything we can match at layer 3 or layer 4 in the ACL. Okay, next we have the route map. This is going to be our policy. The policy says that if we match the IP address 100, we're going to set the IP next hop over to router 2. So this is the directly connected link between router 2 and router 3. Now once we get past sequence number 10, which is what we define, 10 is the default, there is going to be an implicit deny in the route map. But what is different about policy routing versus other applications of the route map is that implicit deny doesn't mean the traffic will be dropped. It means that the policy route does not apply. So it means to look at the normal routing table as opposed to looking at the policy route. And we'll be able to see this when we look at the debug IP policy on router 3. This will show us what traffic is getting classified and which traffic is not. So last step, we apply it to the link level. IP policy, the route map's name is policy. We don't specify a direction because it's only for inbound traffic. The policy routing is always inbound. The other option is for locally generated traffic, if we say IP local policy. So let's look on router 5. We should see now that the normal trace route follows the normal path, so it goes from 3 to 1. But with the addition of the source, now router 2 is also in the transit path. So basically, router 3 is intercepting this particular traffic flow and saying that this is subject to the policy routing. We can see this if we look at the show route map. What are the particular hits? So it says that there were 6 packets matched. Or if we look at the debug IP policy. So we'll debug IP policy on router 3. Let's do a ping to router 1. Okay, these 5 packets come in. Router 3 says the policy was rejected because there is no match. So now we have normal forwarding. So as you can imagine, for every single packet that comes in, if we need to check the policy route, there's going to be some performance hit as opposed to just going to the Ceph table. Okay, next let's look at the ping that is using the source and the destination as we defined. So source is 10.155, destination is 10.111. Router 3 says that there is a policy match. So we're forwarding to the gateway 10.1.23.2, which is router 2. If we were to look at router 2's interface for incoming traffic, we would see that the packets from router 5 are then being received in that link. So we can't necessarily see it with the ping unless we did a debug IP packet on a hop-by-hop basis, but we can tell this based on the trace route. Okay, so a pretty simple policy on router 3 here. If we show run section route map, we see the command at the interface level is IP policy route map, then the route map's name. The actual policy itself is saying that if the access list match is true, then we're modifying what the next hop is going to be. So we're not sending it to the routing table. We're doing this manual overriding. Now again, we could also classify, instead of matching on address, we could match on incoming interface. So on router 3, we could say any traffic coming in from router 5, I don't care what it is, I want to send that to router 2. We could also say set interface, so to change what the outgoing interface is. Normally you would only want to do that on a point-to-point link, because you can end up in problems with layer 3 to layer 2 resolution. Because with Ethernet, we would then need to know what is the MAC address of the final destination. So for non-point-to-point interfaces, you should say set IP next hop. For point-to-point links like a tunnel or a point-to-point serial link, you can say set interface. Okay, there's also some advanced options here if we say under the route map, set IP next hop. We can say set IP next hop, but also we want to verify the availability. Okay, this is what, so we'll say for this hop, sequence to insert into the next hop list. Let's say this is priority number 1. And we're going to call a tracked object. So this is now where policy routing can integrate with the IP SLA agreement. And we'll say that if some condition is true, we want to send the traffic over to router 2. But under other circumstances where the tracked object is down, then we do not want to send the traffic to this particular link. So we could say, based on the just reachability to the neighbor, we could do a basic ping between them. We could do all sorts of different stuff inside the IP SLA. So if we say IP SLA instance 1, IP SLA monitor 1, the type of sampling, the most basic one would be just the echo. Okay, echo is going to be for a ping. So it's ICMP echo. But we could query the DHCP server to make sure we have we can get an address through DHCP, that we can get a DNS response, that we could get a TCP connect. So maybe we're running some TCP application like Telnet. We want to make sure that we can get an open session. We could make sure that we could get a particular page from a web browser. So this would be tracking, is the web server up? So is the server itself up? Does it respond to pings? But then also is the Apache service running, or the IIS service running, where we actually can serve the application down to the end client. So there's a lot of detail you can do here. We're not going to get into too much of it configuration-wise. If you look under the iOS 12.4 or 12.4T configuration guide, there's a full section that is dedicated just to IPSLA if you want to get into more detail as to how this particularly works. But basically the logic here is, let's say that we want to do some sort of ping. We'll say type is echo. Protocol is IP ICMP echo. And we're going to ping the, let's say, 10.1.23.2 address. We're going to ping it every 5 seconds. And we're going to wait 2,000 milliseconds for a timeout. Okay, so we're pinging this address that is connected to router 2. We have our SLA instance. It's called number 1. we're now going to tie this to a tracked object. So we'll say object number 10 is calling the SLA instance. They actually call it the response time reporter here, number 1. Okay, we'll leave all the default values. You could change this if you wanted to change the delays. So how fast is it going to respond? We're just going to leave all of the defaults. So if we show run sections IPSLA or track, this is how we're doing our application testing. So we're saying ping router 2 every 5 seconds. If you don't get a response within 2 seconds, then you're going to declare the object down. Now normally you would want to give it some leeway. Maybe you say if it doesn't respond within 2 seconds, you want to try this many more times. But you can get more detail as to what the checking is actually doing. A next thing we would do is actually start the instance. So we'll say IPSLA monitor 1, or IPSLA monitor schedule 1, start now. And the lifetime is forever. Okay, so I'm just starting the instance and it's going to run indefinitely. So if the router reboots, it's going to continue to go. Now also what this told us, it says the state of the tracked object went up. This means that the ping to router 2 was successful. Okay, but let's look at some situations where if we didn't use the SLA, that our policy route could be wrong. So from router 5, when we do the trace route to 1 from our address 10.1.5.5, the traffic is being redirected to router 2. Okay, that's based on the policy route. Let's say we do a ping. We're going to do the same thing, just ping instead of trace. And we're going to set a high repeat count. Okay, so we're pinging them over and over and over. We can see it's successful. But if we were to go to router 2 and shut down this link, router 3 is not going to know this because, ooh, and I should have undebugged there. Let's see, router 3's console may be locked out now. So the interface is shut down on router 2, but since these routers are not physically connected over the link, it's not a physical point-to-point Ethernet link, router 3 is not going to be able to detect that. Now we could see the EIGRP adjacency goes down, so if we were using normal dynamic routing, we would be able to adapt to this circumstance. So we just route to whatever the available backup path, so maybe we have a feasible successor, or we just route around to whatever new successor that we recalculate. But in the case of policy routing, this is 100% manual. So router 3 doesn't know at this point that the next hop 10.1.23.2 is actually down, but we're still forwarding traffic out that particular direction. Let's see if it stopped debugging. Okay, so the debug is off, but we can see now the traffic is still getting dropped. So this is where the tracked object is going to help us out. So the IPSLA instance knows that the neighbor is no longer reachable because the pings are timing out. So if we were to tie the tracked object to the policy routing, this is now giving us a way to dynamically adapt to the situation. And if the next hop is down, we could say start forwarding to the normal routing table or go to some other default destination. So let's look at what we have under the route map here. So under route map policy, we're not going to set the next hop. Instead, we're going to say set IP next hop, verify availability, 10.1.23.2. Okay, this is the first hop in the list, so you could do multiple ones and check multiple SLA instances. And I'm going to track object number 10. So now what this is going to say is that the policy routing will be true, and we will go towards 10.1.23.2, but only if tracked object number 10 is up. So if we look at the show track, it says the state is down. which means that the policy routing match does not occur now. And if we look at router 5, we can see now the traffic is getting through. If we were to do the trace, it follows the normal routing table. So once this interface comes back up, we should see that the tracked object is going to change its state to up. So now the pings are getting through. It says state is up. Now if we look at the trace route, it's going to go through router 2. So it's still a manual configuration that we're defining what type of traffic are you classifying and then what are you going to do with it. But we're adding more intelligence to it, where previously it used to be that if your policy route was wrong, you just ended up dropping your traffic, and then you would have to manually go into the router and remove the policy. But with the SLA, it's giving us some ability to see, is that next hop or is that interface actually up before I tried to send the traffic that particular destination. Okay, there's also a way that we could check this based on doing static routing. So let's say we're going to go to router 2 and we're going to do the same type of operation. Okay, we're going to change the result of this trace route from router 4 to 1 based on static routing on router 2, and we'll also add some reliability to this. So on router 2, the first thing I'm going to do is just create a static route. I'm going to say if you want to get to 10.1.1 exactly, so this is an exact host route, send the traffic out to router 3. Okay, so pretty basic config, just a static route for this host. You want to go out to router 3. So now from router 4, if I were to do a trace there, we can see router 3 is in the transit path because we're statically routing it to that destination. The problem is now that if router 3's next hop goes down, so we shut down the link between 2 and 3, router 2 doesn't notice this because it's not a physical layer 2 circuit between them end to end. And now the packets are going to get dropped. So they go from 4 to 2. 2 is trying to send them towards 3. But 3 is not up. Its interface is down. So we could use the IPSLA instance for the same type of tracking here. So let's bring the interface back up. And on router 2, we're going to create an SLA instance. We'll say IPSLA monitor 1. The type is just an echo IP ICMP. Type echo protocol IP ICMP. And we are pinging router 3. A frequency is 5 seconds. Timeout is 2 seconds. Next, we'll start the instance. So IPSLA monitor schedule. Instance number 1, we're going to start it now, and it's going to run forever. If we look at the show IPSLA 1 collection statistics, maybe it just may be collection, no. Show IPSLA monitor collection statistics. Okay, this tells us what is the current state of the operation and what's going on. So it says that number of successful operations is 5. So that means that the last 5 pings went through. If we look at just the statistics, this is going to show the current output. Latest operational return code is okay. It means the current ping is fine. Okay, so the object is fine. So next the SLA instance is fine. Next we're going to tie the object to the instance and then call that from the static route. So we'll say track number 5 is RTR instance 1. Okay, these numbers are only locally significant. Usually it would make sense to match them up just for simplicity, but I'm putting them separately just to show which number is being called where. So now on the end of our static route, we're going to remove the old static route, put it back in, but at the end we're going to add tracking to this. We're tracking object number 5. What this basically says is that the static route can now only be in the table if the state of object number 5 is up. If object 5 goes down, it's withdrawn from the table, and then whatever is left over is going to be the route to the destination. So it could be another static route that was a floating static route, could be a default, or it could be any other dynamic destination. So if we look at the result here from router 4, we do a trace. Right now the traffic is going through router 3. So we'll ping 10.1.1.1. We'll give it a high repeat count. Okay, we can see the traffic is going through. Once we go to router 3 and shut the link down, we should see that it's going to reconverge based on the ping timeout. It may take maybe 10 seconds or so at the worst. In this case, it was 8 seconds. But the kind of neat point about this is that we're now adding dynamic convergence to a static route. If we look at router 2 now and say show IP route static, we can see the static route is not in the table. Because the tracked object is down, it's not allowed to be installed. Once the link comes back up and the tracked object state goes up, we should see that now the static route is installed. So let's look at our final configuration for this. We'll show run section IPSLA track or IP route. And sometimes these features are referred to as reliable policy routing and reliable static routing. Because we're tracking the object, then whatever we define as the application that's being tested, that's what determines whether the policy route or the static route is actually being used. So again, in this case, we're saying ping this address. Okay, ping that address every 5 seconds. We're going to wait 2 seconds for a response. If we don't get the response, object number 5 is going to be declared down. Since object 5 is referenced from the static route, it then means the static route has to leave the table and will fall back to whatever other match there is for 10.1.1.1, or whatever the next longest match for 10.1.1.1 is.